This is Mac 1105, section 4.5, which were the log word problems. This last video is specifically on radioactive decay. We have already seen this function, this formula for radioactive decay. This we used in the last couple word problems of the last video. This was the formula for carbon dating. This is a different function. Each function is based on this formula, but it has a different K value. And where that K value comes from has to do with what the half-life is of that particular material. In this case, we're talking potassium 40. You are given this formula. So it says the function A equals A sub 0 e to the negative 0.52912 t models the amount in pounds of potassium 40 stored in a concrete vault, where T is the number of years since the potassium 40 was put into the vault. If 300 pounds of the potassium are placed in the vault now, how much time will need to pass for only 120 pounds to remain? How much time means we are looking for T, just like we were looking for T when you were asked on the last video about how old the skeletons were. So we've got our function right here. I'm going to bring it down here so I can work with it. And we can start plugging in. Remember, we are looking for T. A sub 0 is your initial amount. So we're putting 300 pounds in a vault. That's our initial amount. E stays E, negative 0.52912 T. And that equals A, which is the amount that's left after this amount of time. And that is 120 pounds. So to solve this, we know we've got to get the E to the power here isolated. And we do that by dividing both sides by 300. And this works out to be 0.4. And all we have over here now is e to the negative 0.52912 t. And we know to undo e to the power, we're going to take the natural log of both sides. And I leave this as ln of 0.4 for right now. That's going to cancel. We have negative 0.52912 t. Simple equation now to get the t alone. Divide both sides by negative 0.52912, negative 0.52912, which is going to cancel, leaving the t. And this is now when I would use the calculator. We could have done ln of 0.4 earlier, but it's going to be a long decimal, and rather than having to write all those digits down, I wait to the end to do the arithmetic. Remember, with your calculators, when you hit ln, you get a front parenthesis. You've got to be sure you close off that parenthesis before you divide by the negative 0.52912, which gives us 1.73 if I round it to the hundredths place equals t, meaning it's going to take 1.73 years for this 300 pounds of potassium 40 to decay to only 120 pounds. Uranium-238 has a half-life of 4,560 years. If 800 grams is present now, how many grams will be present in 120 years? We are looking for the number of grams that are left. We are not looking for the T. We are looking for how much is left after 120 years. This is a more involved problem. This requires us actually to do two separate problems. We're going to still use our formula, A equals A sub 0 e to the kt, and we're going to plug in what we know. We know the half-life is 4,560 years. That's our T. 800 grams is present now. That's our A sub 0. So we've got A sub 0, which is 800, e to the k, which I don't know, times 4,560. Now, it looks like we don't have enough information. We know we're looking for k, and right now it looks like we don't even know what a is, which would give us two variables, but that's not true. Remember, the 4,560 is the half-life. That means after 4,560 years, that half will remain, which means for our problem that the 4,560 is our t, and after that much time goes by, half of this will remain, which means the final value is 400. And then I can solve the problem like I did a minute ago, divided both sides by 800, gives me 1/2 equals E. I'm going to put this in this order, 4560K. Now, this is not strange that this is a half. This is half-life, so this is actually a shortcut that you could use. Anytime you are asked for this kind of problem, you could jump straight to 1/2 equals E to the whatever your half-life value is times K, and then solve this. So we will solve like we did on the last one and get the natural log of both sides. I'm going to go ahead and write a half as 0.5, just be easier in the calculator. And then this is ln E, cancels out, gives me 4560 times K. To solve for K, divide both sides by 4,560, and that is my K value. So plugging this into the calculator, ln 0.5 divided by the 4560. When you plug this into the calculator, you get an answer that is in scientific notation. So this is what your calculator says, negative 1.5200, etc., and then E -4, which means negative 1.52 times 10 to the -4, which means move your decimal place 4 places to the left, which gives me this as your K value. Negative 0.000152 is my K value. And I'm keeping all those digits because the more digits you keep, the more accurate we're going to be. Now, we're not finished. That is the K value. Just like we had back here, this right here was the K value. Well, you were given that K value. In this problem, we had to do some work to find the K value. Now that we know the K value, we've got to go through and do the problem again using this formula again, A equals A sub 0 e to the kt. This time we're going to plug in the fact that we're starting with 800 grams, e to the k, which is negative 0.000152, times t, which is 120. And this is just a matter of plugging directly into your calculator because you're trying to find how much is left, which is your A. And this works out to be 785.54 grams. You may be asked to round to the nearest whole number. You may be asked to go to one place, 2 decimal places. I'm not sure. So let's look at another one like this. This one now we have arsenic 74 has a half-life of 17.5 days. If 80 grams is present now, how many will be present in 12 days? This is the exact same problem with just the fact that now it's arsenic, which has a different half-life. So here's the same formula that we're using. So we have A equals A sub 0 e to the kt. Half-life is 17.5 days. That means after 17.5 days, that half will be left. So we are starting with 80 grams, e to the k, which I don't know yet what the k value is for arsenic, times t, which is 17.5. And what goes over here for A is 40, because after 17.5 days go by, half of this sample is left, which would be 40. And to solve this, we've got to get the exponential part isolated, divide both sides by 80, gives me 1/2 e to the 17.5k, and then I have to solve this by taking the natural log of both sides. And now it's basically arithmetic. I'm going to write this as the decimal 0.5. Cancels out, gives me 17.5k. Divide both sides by 17.5, which cancels out, and I get the k over here. When you do this arithmetic, don't forget the parentheses, that you get the front parenthesis when you type ln on the calculator. Be sure you close off the parentheses, and this gives me negative 0.0396 for my k value. And then I have to go through the problem again using the formula. The second time through is just to stuff it in the calculator kind of problem. We are starting with 80 grams, e to the k, which we discovered was negative 0.0396, so that's the k value for arsenic, times 12, because we want to know how much is left after 12 days. Stuff all that in the calculator, and this works out to be about 49.7 grams, or perhaps 50 grams if you are asked to round to the nearest whole number.